So if you can think of like MapReduce as maybe assembly code, just the lowest level kind of brute force API, and the Spark core API as something like, okay, Java or Python, a sort of programming language environment, you can think of these things as standard libraries. So, you know, why did people like Perl back in the day, right? Perl is like a little bit of a clunky language, but it came with all these awesome standard libraries that you can use to do anything. And that made it really a winner for a lot of people. And actually, tons of systems are still written in Perl today, even though it's definitely an old language. So by having these kind of powerful standard libraries come with the core Spark API, it enables users to compose different types of functionality and get out-of-the-box features that they would have a lot of trouble implementing, certainly in MapReduce, but even implementing in terms of the core Spark API is non-trivial, and that's why we've kind of done it for you. So I'm just going to go over each of these, and then I'll end by talking a little bit about Spark 1.0, the release that's about to come out. So Spark streaming, why do people need streaming computation? Well, many problems that people want to solve today involve sort of incoming real-time streams of data. So there's tons like site statistics for internet sites, that's one of the biggest use cases, fraud detection, online machine learning, these types of things. And to build and scale these is challenging. You want to integrate it with your offline analytical stack. You want to have fault tolerance, which for streaming systems is pretty difficult. And you want to have good throughput and high efficiency, because if your system can't keep up with the rate at which you are generating events, then you're in serious trouble. And especially if you have sort of major events, that's exactly when you want your system to be doing well. Because when you have 10 million users come to your site in one afternoon, all of a sudden you want it to still work. That's kind of the most important event. So the way, from a high level, that Spark streaming works is it breaks down streams into very fine-grained batches. So it's sort of a unique approach to stream processing, where you reason about streams and windows of time by looking at kind of 1 to 30-second batches of data. And each batch ends up looking a lot like a normal Spark job, which is that it does some immutable, it has an immutable input, it does some immutable transformations, and you can kind of rerun it in a fault-tolerant manner. So I'm just going to flash kind of what the API looks like here, but you can see it's very similar to the core Spark API. You're doing things like mapping to extract some fields, you're doing group bys, it adds some window functions to say things like I want to get access to a rolling window of the last 30 seconds of data, but all of these are taking and giving RDDs as the main sort of language of interchange. So you get this nice integration with your offline jobs and your online jobs at the same time. And the nice thing about writing this as a library on top of Spark, instead of writing it as a standalone system, is that from an architectural point of view, you get all of this stuff kind of for free. You get the data model of RDDs, you get the way that Spark does intelligent partitioning and shuffling, the kind of optimizations that have gone into task scheduling, the UI and monitoring capabilities, and all this stuff. You just get it out of the box, because the way this is implemented is as a library in the context of a broader runtime and not as a standalone system. So one example of this is we've just added a bunch of machine learning capabilities and SQL capabilities, and you can use these inside of data streams directly. You don't need to now have sort of another project that just exists to only integrate these two types of systems. They just kind of happen out of the box. So the next one I'm going to talk about is Spark SQL. By the way, I'll cover the first two of these in more detail, and then ML and graphics I'm just going to go over really quickly. So Spark SQL is a new feature that's coming in the 1.0 release. And what this lets you do is assign schemas to your existing RDDs in a way that then allows you to exploit those schemas when you're querying the data. So here's a simple example. Scala has something called a case class. You can think of it just like a struct or like a Java bean. It's a simple class that just has, it's not nested. It has only a set of objects inside of it. So if we have a case class called person, we can create an RDD that loads a bunch of data from a text file and maps them into person objects. And then we can register this as what's called a table. And Spark SQL knows how to infer that this has a schema and understand the names of the fields and so on. So once we've done that, we can actually use SQL to write our sort of Spark transformations. So we can take this set of people, which is just a normal old RDD, and use a SQL function to actually call express computation in terms of the SQL dialect that will then compile down to the normal Spark API. And many people are more comfortable writing selects and filters like this, then they are writing it in Scala or some other language. And then once we get back the result, we can also extract fields from it, even using the normal Scala API. So there's kind of a complete interchange and flexibility between these two representations of the computation. And lastly, it's added a sort of link-like API. For those who are familiar with this, this type of API, it's being able to do where clauses as functions where you pass in some kind of predicate into them. So you can play around with this if anyone's interested. There's pretty good docs online. Another nice thing is that this helps with our import and export capabilities a lot. So if you've gone through the effort of describing your RDD with a schema, you can now directly save that as a Parquet file, and it will take advantage of all of the nice serialization format that Parquet has. And I think eventually we'll add support, I don't think it's in the first release, for doing sort of nested and complex schemas inside of Parquet as well. I think for now we only support flat schemas. Is that true? Yeah. Another thing is that you can just point this at existing Hive warehouse. We've already done all the effort of describing your schema, and then you can load data from Hive as a schema RDD. And you can even cache that in memory and then call SQL on it inside of the Spark job, or just use the normal Spark operators on top of it. So it takes advantage of some in-memory columnar storage techniques. A lot of these are borrowed from the Shark project. To give a little bit of calibration, Shark is a separate SQL engine that is built on top of Spark, but it was never distributed with the Spark project because Shark pulls in all of the Hive code as its way of the way it works is it takes the Hive operator graph and recompiles it down to Spark, but it does pull in a lot of dependencies from Hive. So what we've done with Spark SQL is taken a much lighter weight approach where we've built some from scratch SQL support inside of Spark, and over time, Shark will actually be refactored to just leverage this SQL support instead of having its own from scratch operators. So next project I'll just mention briefly, the last two is MLlib and GraphX. So MLlib was released in Spark 0.9 a few months ago. It is a set of popular machine learning algorithms directly implemented in Spark, so you don't have to re-implement them. And what's important to note here is that it's not a grab bag approach where there's a bunch of things that were contributed and they are varying in quality and varying in kind of how optimized they are. We went with the opposite approach, which is that we have a small number of optimized and very rigorously reviewed algorithms that are explicitly designed to take advantage of all of the performance of the Spark API. So this is kind of a highly curated library that we're standing behind and supporting as a project, and not kind of a grab bag of things of varying quality, which is kind of some other Hadoop projects have taken that approach. So last I'll talk about GraphX. So GraphX is maybe similar to MLlib. The idea with GraphX is to let you reason about graph problems in a way that exposes a native API that understands things like edges and vertices rather than you having to write this yourself. Let me give you a quick example. So I might load some data from a file that has a bunch of edges in my graph and another piece of data that has a bunch of vertices. These are Spark RDDs. I just hand it to GraphX by saying create a new graph with these edges and these vertices, and then I can call PageRank directly on that. So PageRank is a built-in graph function. It's a very popular graph function. It's how you compute the web popularity graph. It's one of its well-known uses. This is kind of the way you could think about using these libraries, is you can do your ETL and other things inside of the core Spark API, and then you can hand off the hard part to a Spark, a sort of existing algorithm to take care of what you're trying to do. So why is this unification beneficial? Okay, so it's beneficial for us as developers because the amount of code that we have to put into these projects is sort of diminishing with each new thing that we add, because more and more functionality, useful functionality, ends up in the core. So this graph compares Spark to a bunch of other sort of execution engines. Some of these are very domain specific and only for one thing. And it's how many lines of non-test code there is. Okay? So this is the core Spark API on the right. And this is how much incremental code was required to add Spark SQL. This is how much code was required to add streaming. And this is how much is in the GraphX library. So as we add new libraries, we make improvements and increased functionality in the core that enables us to have a very powerful core runtime that where the marginal cost of adding new functionality is small. So you should think, if you're a library writer, if your company is going to have some, maybe even other domain-specific tools, you should want to go to a platform where you can write that in a very concise And as a result, even with all these higher level libraries, Spark is smaller than even the smallest of these other projects that are much more domain specific, that are focused on just query processing or just graph processing. And we can also do pretty well on performance. So Spark can be competitive in many cases with these extremely domain specific solutions to all of these problems. It may not always be the very best, but it's at least competitive, and you can use it for many different types of things. That's kind of the project philosophy we have in building Spark. These are just a bunch of performance graphs that have been from other talks, and most of these are from papers that you can look at. But the benefit for users, so that's why it's nice for us as developers, right? But why should you care? You're just a user. You don't care how many lines of code maybe is in the system. Although you should, because it's a proxy for how simple it is. So for users, you can get this really high performance data sharing. So I said at the beginning of the talk that moving data between different jobs and workflows is often the bottleneck in many types of data analytics settings. So by avoiding that bottleneck, by going through abstractions like a persisted in-memory RDD, you can get huge optimizations and performance improvements, and also just decrease the complexity of your data pipeline a huge amount. Also, you can compose models. So you can do some ETL in the Spark API, and then you can take that and do machine learning on it, the result, or run some SQL queries on it, or do whatever you want. You kind of have this composability built into the library, which is exactly going back to the Perl example, why everyone loves a general programming language with good libraries, is because you can take some data, you can use Perl to write to some SQL store, and then you can get the result, and use some other library to do something on it and write it out. Like you can basically mix and match different types of standard libraries. And you also benefit from the shared investment in having a really good core runtime. So it's like, why do people run applications on the JVM? Because there's like hundreds of millions of dollars of investment in making the JVM really good every year. So if you run an application on it, you automatically get all the benefit of this. We don't have hundreds of millions of dollars going into Spark at the moment, but it's maybe someday it'll be at that scale. So just to end by talking quickly about some new releases. So Spark 091 was actually released today. We just sent an announcement to the dev list. This is a maintenance release, so everyone who's running 090, which was previously the most current release, we recommend that they upgrade immediately because it just provides extra bug fixes, more stability, etc. Spark 1.0 is going into code freeze this week. It's why I'm a little bit tired. The official code freeze was last night, so I was up very late. And we're in a QA period now where we're doing some testing on the release. It'll probably come out end of April, approximately. It's a community voting process, so we can't give an exact date, but it's going to be roughly end of April. What are the main things in Spark 1.0? This is kind of the forefront, the frontier of the Spark project. So the biggest thing is Spark SQL, this project that's kind of a from-scratch SQL engine inside of Spark. And that's coming also with Java and Python APIs, so we're pretty excited to get those out in the very first round of this. Some other kind of exciting things, we'll be supporting Java 8's Lambda syntax. So for those who are familiar, Java 8, in many ways inspired by Scala, has added a syntax where you can express anonymous functions very concisely with using some types of type inference, basically. And that's really important for writing data analytics workflows where you're kind of passing a lot of functions to something like the Spark API, and we'll support that. So we also, in our ML library, are supporting sparse types of inputs. So there's a whole class of ML problems, especially at very large scale, where the input matrices are sparse, and you need to actually totally design APIs differently to handle that case, both the APIs and the algorithms. And we've introduced sparse support for a bunch of existing algorithms. We have a history server for our UI. It's kind of maybe sounds esoteric, but in the past, if you finish running a Spark job, the UI would go away because all of the state pertaining to the UI was contained inside of the job itself. And now we have a way where this state can be persisted, and you can keep like a long-lived UI that contains all the results of your Spark jobs. Maybe sounds a little boring, but it's a huge deal if you're actually running Spark in production. It's really nice to have this. Last thing, a couple things. We have API stability, so as you can tell, Spark is not just it's not only an end-to-end application. It's something a lot of people build functionality on top of. We've built some in the Spark project, but there's also many sort of applications that are built directly against the Spark APIs. So providing API stability is really important to make those people confident that they can invest in Spark and they can upgrade to new Spark versions and everything kind of still works. So that's also in this release. Although we've done a pretty good job of API stability in general, but we're kind of putting it in an And lastly, we've improved, I mean, this is just a small list, but a bunch of stability stuff around running on Yarn. We now are working with like the most recent stable Yarn APIs, etc. So I'll just wrap up, and then we can take questions. If you want to get started with Spark, the best way is just to go to the website. We invest kind of a lot in like documentation and tutorials and this kind of stuff. So you should have tons of content there if you want to get started playing around with Spark and getting your hands dirty. It's easy to run in local mode on a managed cluster on EC2. And I just wanted to make a shout out. We have a Spark Summit this summer. We had a small Spark Summit earlier that was the first one ever, and this is coming about 6 months after that. It's going to be much bigger and kind of like the first really large-scale Spark event that has ever happened. So definitely I would love people to get involved in that and consider coming. Cool. This is just a conclusion slide, but I won't talk too much about this because we've already maybe gone over our time slightly. But so yeah, with that I'll close, and Ravel and I can share any questions that you have. Thank you. Sure. So okay, the hand up right there. Yes.
Can you put up these 4 slides before the unification code?
Sure.
Yeah. So what program actually took 120,000 lines of code?
Which program is 220,000?
No, 120. Is that what?
This is Hadoop MapReduce. So
Okay.
this is the most mature, to be fair. It's the mature project. It's probably many, many years of work on it. It's also written in Java, so there's some inherent bloat in the code from that.
So this is the entire framework.
This is just the MapReduce engine, so it doesn't include the file system and the other
So you're
stuff.
just comparing that to the one written in Spark.
Yeah. Yeah. Yes.
So, question, this is all about Spark. What is afterwards? This data system.
Yeah, so okay, good. Oh, by the way, I didn't repeat the first question, so I'll try to do that in the future. But she was asking to repeat. Oh, I did? Okay. Okay, so the second question is, okay, so this is Spark, that's great. But we both work at Databricks, so what is Databricks doing? So Databricks is doing a couple things. One side of the house is the open source work. So we're deeply committed to Spark, as you can tell. We are investing a ton of resources in Spark, and we're keeping Spark obviously 100% open source. We've given Spark to the Apache Foundation, and that's the way we're going. It's not the company's not forking Spark and having Spark plus that you can pay more for or something like that. So the product strategy of the company is around Spark, but we haven't actually announced the key product offering, and it's something we're in sort of stealth mode at this point with regard to that. So unfortunately I can't say much about the product side of the house. One thing I can say is that we're partnered with Cloudera to help do kind of on-site support for Spark. So if you want support for Spark, you can go to Cloudera, and they, with a pure partnership with us, are supporting it and also getting involved in the development. But that's as much as I'm at liberty to say at this point, unfortunately. Sure.
Is RDD the most generalized data model in terms of not just the computation that we are handling, but in terms of things which are stored in a distributed file system?
So if I understand the question, is RDD the most general data model that compared with other file systems?
Is there a limitation by going the RDD approach, or is it just like it kind of provides a larger set of operators, does it also shrink something else in terms of value?
I see. So I guess the question is, so RDD is an abstraction. Does it make any sort of sacrifices in terms of the abstraction that limit you from doing certain things potentially? So I would say the RDD is a very, very general abstraction, so I don't think we tie our hands too much. One thing that's true of RDDs is that they're immutable, and that's kind of a very common property in many of these analytics frameworks, like HDFS files are immutable. And so it's not like an OLTP kind of thing where you can maybe do very fine-grained mutations to it because it's hard to achieve fault tolerance in that setting. So that is one thing that is maybe slightly restrictive about the API, is that we kind of make assumptions that there are these immutable data sets. But other than immutability, there's almost no assumptions we make about it, so it's fairly general. In the front.
About Yarn support, is there like also coverage for the Spark streaming and Spark GraphX for the Yarn support, and is it ready for the prime time, so you have customers running it in production?
Yeah, that's a good question. So let me reiterate it. So the question is, for Yarn support, do things like Spark Streaming, Spark GraphX, these other libraries, are they different running on Yarn, or are they ready to run on Yarn and stuff like that? So the nice thing about the way Spark works on Yarn is that it actually is running exactly the same code that runs in any other Spark environment. The only step that's different is initializing all of the job, getting the resources and stuff is managed by Yarn. So this thing was already abstracted inside of Spark because it used to run initially only on Mesos. Then we abstracted it. We had a built-in resource manager that would ship with Spark, so you didn't require Mesos. And now you can run it with Mesos and Yarn and in a few other ways. So that resource management dimension is very orthogonal to what the application is actually doing. And so running Spark on Yarn is not super different than running it elsewhere. But that said, there are still things we've been fixing and stuff like that, but mostly it's just about launching the application, making sure that works well. Once it's up and running, it's the same code. Yeah. Sure, next question.
Do you have any production systems? Anyone using Spark at all?
Oh, so are there people using Spark in production? Yes, there are. So, I mean, Spark is like actually a somewhat mature thing now. So it's been out for many years. And there's companies we work with directly, like Yahoo, that run Spark in production. There's also, if you go to the Spark website, we have a powered by Spark page. So all the companies kind of voluntarily talk about what they're doing with Spark there. And you can go there, it's kind of cool. You can see the companies, and then also they'll say, like, here's what we're doing with Spark. And so you can learn a little bit more about it.
So it's kind of my
Go ahead, Reynolds.
Hello. It's kind of my bad. I think I missed one slide on that. It's being run in production in a lot of places, including some of the largest clusters and telcos, internet companies, small startups, some organizations that don't look at your data ever.
Yeah, we usually have a slide with all the logos, but I guess we can show it. Actually, yeah, sure, in the back.
Question about graphics. Like, if you write those algorithms from scratch, or you're calling established libraries already that do this network effects?
Do you want to answer?
So most of the algorithms that we can, the question was about GraphX. Did we write the graph algorithms from scratch? So yes, the reason is most of the existing graph algorithms are implemented for a single node, and they don't really work when you run them across multiple nodes. So most of the algorithms were rewritten from scratch. But GraphX provides a very nice graph abstraction that makes it very easy to program. It's kind of comparable to the Spark high-level operators. So it's actually not too, like we wrote PageRank in like 5 lines of code.
Sure, how in the front.
So is there a huge speed difference between which API you choose? You had Python in statements, and those aren't very fast. Do you guys abstract that away? Or
Yeah,
is
sure.
that
So
in Python?
let me explain. So the question is there a speed difference between the APIs? So if I write in Java, is it different than if I write in Python or Scala? And the answer is that Java and Scala are the same. They both come right out of the JVM. The Python code might have some performance degradation because you're running in it runs in a CPython runtime. It's not running in Jython or something like that. And the real bottleneck actually in that case can be the serialization cost of sending data around, serializing Python data and shipping it and allowing Spark to ship that data across the network. So there are some performance, if anything, I mean, it's always, it depends exactly what you're doing, et cetera. But in general, Python might be a little bit slower than the other APIs, but not by orders of magnitude, maybe some small amount slower.
One exception, yeah. There's one tiny exception, which is for the Python numbers. If you use, for example, NumPy on a whole bulk collection of data, because that's calling native code, you might end up being faster than JVM.
Oh yeah, fair.
So we can use NumPy.
Yeah,
SciPy.
So the reason why we went with CPython, so it just uses a normal CPython runtime because we want to be able to use all the native libraries, SciPy, NumPy, these things. But yeah, I guess that is true. Sometimes they can be faster since they have more efficient native routines. Yeah. How about all of it in the back? Just
For heavy use of in-memory computing, what do you recommend is the amount of scratch space to keep in RAM? What's the sizing between the data set and the amount of scratch space? And also, what do you recommend in terms of biasing towards more cores on a given machine and less machines to reduce the network traffic versus throwing
data set and I'm trying to size my Spark cluster, how do I think about how much memory I should have relative to the size of my data? The other question is, in general, if I'm sizing a cluster, how do I think about having sort of beefier nodes with a lot of CPU and maybe a ton of RAM versus having more small nodes that maybe have the total same aggregate capacity, but they have sort of less resources each. Is that right?
And also the ratio between CPU cores and memory.
Got it. And what is the right ratio between cores and memory? So those are all good questions. I think on the sizing bit, many people try to size the cluster so that their critical data sets actually fit entirely in memory. So if you want to have less than the entire data set in memory, you'll get a nice like linear degradation. But in many cases that we've seen, like the cost of memory, the combination of the cost of memory and the importance of this data to the customer means that they're actually like willing to buy enough memory to keep all of their critical data in memory. The second question is kind of, do I want to have a few really beefy nodes, or do I want to have many more smaller nodes? And we've definitely seen people err on the side of a few beefy nodes, and the reason is that the network traffic can actually be the bottleneck in many cases. The only thing to watch out for are twofold. One is that the JVM doesn't love to exist with like a 350 byte heap because of the way that it does garbage collection. So in those cases, sometimes people actually run multiple Spark workers on the same node. They'll just actually like run a few JVMs. Because the whole programming model is embarrassingly parallel anyways, it really doesn't matter if you just run a few JVMs just to cut down on the heap size. Another thing that can happen is we interact with the file system a lot, and like if you're reading or writing data, and some file systems don't love to be accessed on a 32-core machine where you're trying to sort of hammer at the file system from a bunch of cores concurrently. You'll run into that problem is in the broader class of like operating systems maybe don't handle really intense workloads on a bunch of cores always so well these days. But that is less and less of a problem. So I would say we've definitely seen fewer beefier machines being used in many settings. And to your other question of the ratio of cores and memory, it kind of depends on your data set. But yeah, so I don't have a great answer for that, honestly. Ronald, do you have any thoughts on that? Is there like a single answer that's useful for people?
I think, yeah, probably profile a little bit. I think probably, it really depends on what you're running. Like running k-means is probably different from running object regression. Running graph is different from
Yeah, that's a good point. Like some algorithms are very compute heavy. So even if you have a small amount of data in memory, it takes a lot of cores to just crunch it. Other things like if you're just doing a scan of the data set to count how many records there are, the compute is going to be very light compared to the memory used. Long answer there, sorry. Sure, how all the way on the left?
MapReduce supports compression using the compression codecs, and you can implement encryption. What are your thoughts with regard to security on Spark?
So there's a question, MapReduce supports compression and encryption. What are our thoughts on security in Spark? So the first thing, compression is like orthogonal to security a little bit. But we also support compression of all of the intermediate data that we write out inside of Spark. We don't use the Hadoop codecs usually. I think we use a separate, faster compression library. But we do compress data pretty aggressively when it makes sense from a performance perspective. On encryption, we currently support authentication as of Spark 1.0, so we can tie into like a Kerberos setting. We're not encrypting the connections between the nodes at the moment. That's a stronger security model that we don't have, but I'm sure that will exist in Spark at some point. We just need to figure out how to use all the sort of right libraries and do it in a principled way and stuff like that. Sure, how about integration?
Yeah, so the curation, you said the core is curated. So is that something, the test suite that's there along with how you're taking care of anything that can go wrong, the scalability of your data? So, I mean, you're providing some test suites to curate, or how is it just the expert opinion or something like that?
So sorry, I didn't totally get the question. I heard, are we providing test suites?
Exactly. For when you parallelize, when you have re-implemented the code for most of the algorithms and APIs, how do you curate them? What is your process of curation?
I see. So I guess it's about like our test environment and how do we make sure this stuff actually works when it's at large scale. Is that?
No, when
You keep saying curate, but I'm just confused. Like, what is curate mean?
maybe talking about machine learning.
How do you verify clustering is correct?
Oh, how do we verify the correctness of the algorithms? Oh, that's a good question. So we do a few different types of tests. So I think like there are many unit tests in these things large-scale tests, but mostly we do those for performance and not correctness, although it's a little bit of both. So yeah, I think mostly we rely on unit testing for that, I would say.
Yeah, so one thing, I think you brought up a very good point, which is how do you test machine learning algorithms at scale or even not at scale? Because machine learning is inherently, sometimes you introduce a bug, it becomes a feature to improve the accuracy of the prediction. I think a lot of the algorithms are becoming, so first of all, they are being worked on by experts. Like we're talking about people who actually invent some of the algorithms, they wrote them themselves. And this is actually becoming one of the most popular review code base. There was this one anecdote I can give you, which we were deciding for Spark 1.0 to choose a sparse matrix vector library. And then in that discussion, we actually got every single author of the matrix libraries on the JVM to come out and participate in that discussion. Everybody wanted to convince the Spark project to use their libraries because they believe it's going to be one of the probably most popular things. So there's a lot of experts' eyes on all of this stuff. And we try to, we started basically working with a lot of different machine learning experts to make sure that stuff's going to be okay. We can get more.
How about the LinkedIn? Sure.
So, RDTs, does it have a storage format attached to it, or is it pluggable, or what is it?
Yeah, that's a great question. So is the storage format for RDBs kind of pluggable? Is it defined? How does that work? So there's a couple of things. So one is that RDBs can both come from various formats and be saved as various formats. We go through the Hadoop input format API. So you can read RDBs from Cassandra and other types of systems, and you can save them back to those systems, to HDFS, to a database, to anything. The intermediate representation that we have inside of Spark is somewhat configurable, but currently it's only configurable in the sense that you can tell Spark to choose from one of a few different options. Because we do some kind of crazy stuff like serialization and compression for the in-memory format of the RDB. So there is some flexibility for it, but right now it's purely inside of the internal representation is purely inside of Spark. Making that pluggable is something we're looking into for future versions. Yeah.
And is it columnar, or?
It depends. So like the schema, if the schema RDBs, we know that there's a schema, so we can do columnar storage on it. For other things, it's just Java objects. We don't know what the schema is of them. So there we do different types of serialization for it. But basically, whenever we can exploit some information about the schema, then we exploit it into storage. Sure, how about in the back with glasses?
Can we specify schema for streaming and apply the Spark SQL on top of the streaming?
So you can apply, so yes, you can. Like you can use schema RDBs in streaming jobs. What we don't have yet is we don't have streaming specific operators in the SQL. So you can't use window functions in your SQL. Although I think there's a project from Intel that proposes this. They have a repository you can go look at on GitHub. But so there's been some people playing with that extension, but it doesn't exist yet. It's a very natural thing to add. Also, I want to be mindful. How much time are we kind of wrapping up here on time, or?
We have time for 3-4 more questions.
Okay, maybe a few more questions, and then
Yeah.
we'll informally be around
Yeah.
after that. Sure, in the front.
So what kind of benchmarks do you provide for like existing customers who are using MapReduce? If they want to try out Spark, what kind of technology can you show them?
Yeah, so for customers, what benchmarks do we have? So we have a performance suite that we run on Spark at every release to do regression testing. We're not as concerned about A/B testing against MapReduce every time we do a release because like we're more concerned about making sure Spark is doing better than previous versions of Spark. But some of these things could be very easily benchmarked against MapReduce. I think what many users do is they take their existing jobs in MapReduce, they take one job, they rewrite it in the Spark API, and they run it on Spark and they see how it does. Because the user they care more about their exact workloads. But we don't have tons of A/B. We've done a few sort of for research papers and stuff, but we don't have a full set of A/B tests with MapReduce because mostly we're just concerned about making Spark really fast. Like it's not that hard to make MapReduce in general, so it's not something we can spend a lot of time focusing on.
For any reference architecture, can you use any benchmark that's available to share?
So the Spark perf regression tests, which is what we run on Spark, those are public open source kind of things. So people can run them. They can also use the parameterization we use when we test our releases and stuff like that. Yeah, so the question is what component in the system keeps track of the lineage and kind of where the RDD is distributed and so on. So there's like a master component, it's called the driver, the sort of centralized component of the application is tracking the lineage of the RDD, and that's actually the mechanism by which we have fault tolerance. We understand the lineage, so if there's failures on a worker node, we can replay that part of the job in a fine-grained manner elsewhere. So if you read this Spark, so currently it's not replicated. So there's certain types of, for very long-lived Spark jobs like streaming jobs, there's a different mechanism where it can be high availability. You can restart this thing and it's okay. But for shorter jobs, if the that driver component is a point of failure at the moment. Although these are like short-lived jobs, so having one link as a point of failure is not, statistically, it's not a big problem. Yeah. Okay, so
Great.
Yeah.
Thank you so much, Patrick. And, they're going to be hanging out for some time, so feel free to catch up with them. And with that, if any of you want to last minute put your cards here for the Edgebase conference tickets,